3 by 3 process was a little bit much. So let's look at what happens when we actually have the application problems. So anytime we do an application problem, it really takes 2 read-throughs to figure out the best way to solve it. So we want to look at what information is given and what am I finding. Then I'm going to assign a variable to what the unknown value is. And a lot of times I know I'm very visual, so I do make a lot of sketches. Then I'm going to write the system of equations with both variables. Then I'm going to solve it and state my answer, and I'm going to ask myself, is this answer reasonable or is it not reasonable? Then, if I'm taking an assessment, especially in the lab, I'm going to want to check my work. So a common geometry problem we see in the lab is working with this rectangular field, and I'm relating perimeter and the different values of length and width. So if I read it, I'm going to be able to assign variables to length and width because I know the perimeter, it's not a variable, but I don't know the length and the width exactly. So I'm going to write a system of equations. The perimeter is going to be 2w plus 2l, because I would add every side, equals 360. Since the length is 20 yards more than the width, this would be described as L equals W plus 20. Once I'm done with that, I can set up that system and solve it through substitution or by elimination. I would prefer substitution because I've already solved for L. So I'm going to complete my algebra and get that W is 80. Once I know that my width is 80, I know my length is 20 more, so my length is 100. Which means my field is going to be 100 yards by 80 yards. If I want to solve money problems, this is an example of a money problem. I'm going to read the problem 2 times. I want to grasp what are the years here, what are the numbers representing, and then I'm going to assign the variable. I'm going to let B be the average cost of the baseball tickets because that's what's varying here. And F is going to be the average cost of the football tickets because they're also being varied here. What do I know? I can write a system of equations because I know 3 baseball plus 2 football equals the 245.52, and 2 baseball plus 1 football equals the 136.50. Then I'm going to solve the system of equations by elimination, probably, is the best way to do it, because I multiply the bottom equation by 2, and then I'm able to add them together, or -2. So once I get the baseball value, I can plug it back into the original equation to get my football value. The average cost of the baseball ticket is $27.48, and the average cost of the football ticket is $81.54. If I want to check my answers, I can plug it back into the original equation to see if I'm right, and I am. The answer is correct. If I want to solve mixture problems, now these are common in the lab. So the grocer has a coffee mixture that's being made, and they want to know how many pounds are being used. So I'm going to assign my variables, and I'm going to say that X is the number of pounds of $4 coffee, and Y is the number of pounds of the $8 coffee. Then I'm going to summarize this using a table just to kind of keep everything straight. I'm going to write my system of equations using what's in the table, and then I'm going to solve it by the methods we did last week. If I have distance, rate, time problems using 2 variables, and basically, guys, what I'm doing is working a problem in the lab. I have the train going, and everyone I know despises the train problem. So the way you would do this is X is your train speed, Y is the truck speed. I'm going to create a nice little table so I can understand what's happening here. And then I'm going to set up my equations based on setting the times equal. Then I'm going to solve my equation, and I would use substitution because we've already solved for X here. So then I get the train is traveling at 60 miles per hour and the truck is traveling at 52 miles per hour. Another motion problem is this canoeing problem that we see. When we do this, we're going to have the rate of the canoe and the rate of the current because they're working against one another. And if I set this up based on what I'm given, this is what I'm going to get in my table. From there, I'm going to have to solve it. So I would go ahead and distribute, and I would use elimination here and not substitution. So that I can get my x variable is 8. I'm going to plug that back in to get my y variable, which is 2. and then that signifies that Shannon's rate in the still water is 8 miles per hour, but when the current is affecting her, it's 2. So if I have a problem with 3 variables and a system of 3 equations, this would be set up similar to this question. This is not a very common question in the lab, so you can take a deep breath. So in this case, I have 3 different products, so I have 3 different variables. I know there are 10 more bottles of the Felice, and there are 3 fewer of the other one. So my total value, if I add it all together, would be this equation. So now I have 3 equations to work with, and I would use substitution because I've already solved for x and I've already solved for z by doing the equations. So once I've done the substitution, I get y as 11. Once I know that y is 11, I can plug back into my x equation and replace y with 11 to get 21, and then I can plug back into my z equation with y to get 8. So these 3 by 3s are not as drastic as the ones in the previous section. If I'm solving a business problem, I can have multiple things going on here too. I have 3 different types of printing that's happening, and I set up the 3 different equations. Unfortunately, this doesn't have it solved for one of the variables already, so I'm going to have to do a little more legwork. So I'm going to eliminate x from equations 1 and 2, and then I'm going to use that equation after I eliminate it with y to create my 2 by 2. Once I create my 2 by 2, then I can solve it like normal for z. I can replace 2z with that 600 and solve for y. Then I can replace z and y and the next one to get the answer for x.